Lastly, let us consider example 5, where we want to determine our node voltages using node voltage analysis. We will proceed with our standard 4-step solution methodology. Step 1 is to assign nodes, where we have A, B, C, and D designated on the schematic on our left, where D corresponds to our ground, as well as our leg currents. I1 runs through a 10 ohm resistor between nodes A and B, and I2 runs through a 40 ohm resistor between nodes B and C. It is noted we have a supernode existing between A and C, and we have a voltage source existing between nodes B and D. Step 2 is to assign our voltage potentials consistent with our passive sign convention, where V1 corresponds to a 10 ohm resistor, where its polarity is dictated by the directionality of I1, and V2 corresponds to a 40 ohm resistor, where its polarity is designated by the directionality of I2. Step 3 is to determine the proper number of KCL equations we need. We have 4 nodes, such that n is equal to 4, and we have 2 voltage source equations. Thus, we need 1 KCL equation, and we'll apply this at our supernode at the top. In doing such, we recognize that we have 5 amps entering, 2 amps exiting, I2 entering, and I1 exiting. Thus, our KCL equation at our top supernode is 5 amps plus I2 is equal to I1 plus 2 amps. Step 4 is to apply Ohm's law to our KCL equation in terms of our node voltages. Thus, our KCL equation becomes 5 amps plus I2, which is expressed as VB minus VC per 40 ohms, is equal to I1, which is expressed as VA minus VB per 10 ohms, plus 2 amps. Currently, we have 1 equation and 3 unknowns. If we look at our top supernode, we can construct an equation. That is, VA would be equal to VC plus 10 volts, or we can say 10 volts is equal to VA less VC. For our bottom voltage source, we have VD being ground and VB being at the negative terminal of a 12 volt voltage source. Thus, we can say VD is equal to VB plus 12 volts, or 12 volts is equal to VD minus VB. In any instance, VD is equal to 0, and VB is found to be negative 12 volts. Thus, if we re-express our KCL equation in terms of VA, VB, and VC, and eventually drop our units, we have the following. 5 amps plus VB minus VC per 40 ohms is equal to VA minus VB per 10 ohms plus 2 amps. Or we could say 4 VA minus 5 VB plus VC is equal to 120. And recalling VB is equal to minus 12 volts, we can make that substitution such that 4 VA plus VC is equal to 60. Thus, we can combine this with our supernode equation in matrix form such that we have 4 VA plus 1 VC is equal to 60, which comes from our KCL equation. We have 1 VA minus 1 VC is equal to 10 from our supernode equation. Thus, we can solve for VA and VC such that VA is equal to 14 volts and VC is equal to 4 volts.